Alrighty, hi folks, we're back with review questions for 7. We'll start with number 1. An object moves at a constant speed. Is its acceleration necessarily 0? Why or why not? So speed's not a vector quantity. It doesn't account for direction. So something could have a constant speed and be moving in a circle. If something's moving in a circle, like in uniform circular motion, it can have a constant speed, but the direction is changing, so velocity can't be constant, acceleration can't be constant, and force can't be constant because they're vector quantities, but the magnitudes of those things can be constant. So acceleration might not be 0 simply because it's changing. Velocity is changing, and acceleration is the change in velocity over change in time. So it could be moving in a circle at a constant speed. Number 2 says this: an object moves from point A to point B. So point A would be here, point B would be here. So it's moving from A to B along that curve. At a constant speed. Draw its acceleration and velocity vectors. Don't worry about magnitude. Alright, so if the object is right here, kind of in the midst of the curve, anytime, even if you're not in uniform circular motion, if you're going in a curve, you are experiencing centripetal force, centripetal acceleration. So you have to kind of picture yourself traveling at some sort of point along a circle. The circle might be kind of more along the path at that point. So your velocity vector is always tangent to the circle at the point you're at, touching the circle only in one place. And your acceleration vector is always perpendicular to the velocity vector pointed in toward the center of the circle. So that's that. Number 3 says, of course, if you're going from point B to point A, the acceleration vector would be the same, the velocity vector would be pointing the other way. I think he tries to trick you on a test by like the same problem going a different direction. He does that all the time. So watch out for just paying attention to the details. Number 3 says, given the force and the velocity vectors drawn in this situation and that situation, which would result in uniform circular motion? So in uniform circular motion, force and velocity vectors have to be perpendicular. So it would be choice A, where they're perpendicular. Number 4 says, consider an object moving uniformly in a circle. If the speed doubles, but the radius doesn't change, what is the new centripetal acceleration? So the last time we had a problem like this on this test, a lot of people missed it because they didn't write down the equation. They just said, well, if speed doubles, force doubles. But in things like the range equation and centripetal acceleration equations, velocity is squared in the equation. So centripetal acceleration is velocity squared over radius. So it says the speed doubles, so velocity doubles. So if I double velocity, that would be 2 squared. It's in the numerator. So acceleration is going to increase by a factor of 4. It increases by a factor of 4. Because if velocity doubles, that double will be squared in the acceleration equation. Anytime you have that on a test, you need to write the equation you're using, and that way you won't be fooled, and I want to see your work. Number 5, a student places 2 objects on a table only a few centimeters apart. They don't move toward each other, so the student says there's no gravitational force between them. Is that true? Well, no. My coffee cup and I have a gravitational force between us. These 2 pens have a gravitational force between them, but the force of friction is greater, so they're not going to move unless they're on a frictionless surface, which basically doesn't exist. Alright, number 6. Newton's third law says that for every force, there's an equal and opposite force. Suppose 2 massive objects are sitting close to each other, right? So these 2 pens, right? This pen exerts a force on this pen. What's the equal and opposite force? well, this pen exerts a force on this pen. So, say Venus and Earth, right? Venus exerts a gravitational force on Earth. The equal and opposite force is Earth exerts a gravitational force on Venus. Always one object on the other. The equal and opposite is the other on the first. Let's see. Number 7 says, you've already been told that acceleration due to gravity is not really constant near the surface of the Earth. It varies a bit depending on where you are. Compare gravitational acceleration at sea level to the tip of Pikes Peak, right? So closer to the center of the Earth versus high up on a mountain a little further from the center of the Earth. Where would you expect acceleration due to gravity to be bigger? So if we look at this equation, right? So when radius goes up, so on a mountain, right, the radius of the Earth from you to the center of the Earth would be bigger. So Pikes Peak, radius would be big. What's going to happen to this number? Well, a big denominator means a smaller number, right? So acceleration due to gravity will be smaller when radius is big. So on Pikes Peak, AC is smaller by just a little. Right? Climb a mountain, lose some weight. So A and R are inversely proportional, so acceleration increases as R decreases. And I said acceleration decreases as R increases. They're inversely related. So show your work, show an equation, show that relationship, right? As radius increases, acceleration decreases, inversely related. Number 8 says, two objects are in close proximity to one another. If the distance between them is suddenly doubled, what happens to the strength of their gravitational attraction? So, distance is doubled. So if we look at the gravitational force equation, radius squared is in the denominator, right? So if radius is doubled, then the force is going to change by 4 times because that 2, the doubling, will be squared, right? But how is it going to change? Well, it's in the denominator, so when radius increases, this side is going to decrease because you're dividing by a bigger number. So the force is going to decrease by 4 times. You need to show that equation. If this is confusing to you, right, you're dividing by a bigger number, this side gets smaller, so force gets smaller. If that's confusing, we can talk about that in class. We'll definitely see that in the lab, I hope. Assuming we can swing the apparatus at a constant speed. That should work. So number 9, an annoying fly travels around your head in a circle. If the fly suddenly increases its speed but stays in the same circle, will the orbital period increase or decrease? And then what about the orbital frequency? Okay, so the fly stays in the same circle but goes faster. So if you're going faster, you're making more revolutions per second, right? So period, the time it takes to orbit, will decrease because you're going faster. And frequency and period are inversely related. So if period decreases, then frequency will increase, right? So we've got period is the time it takes to orbit, and period is 1 over frequency, or you could say frequency is 1 over period. That's the same thing. They're inversely related. Number 10, the spin cycle of an automatic washing machine has the clothes spinning around inside at a high rate of speed. This removes a large amount of the water that has soaked into the clothes. Given the fact that the walls of the washing machine have small holes, explain the physics behind this. Right, so there's a frictional force, but the velocity of the washer is big enough to overcome that. There's no force like tension or gravity or anything that can hold the water in the clothes, right? So when it's accelerated, it's spinning in a circle, its velocity vector will be tangent to the circle, right? There's a circle that's spinning, the clothes are spinning around. Velocity vector will be tangent to that circle, right? And so when the water droplets encounter a hole, right, they will continue to move in a straight line until acted upon by any force, right? So that's Newton's first law. So their velocity is like that. If they get through a hole, they'll just continue until they crash into the side and fall into the drain. Alright, so that's review questions. I'll stop and make a new video for practice problems. Actually, maybe I'll do a couple because I bet this is going to be a long video for practice problems. Yeah, I don't want to erase equations, maybe. Alright, so practice problem 1. An airplane pilot nosedives, then pulls his 455 kilogram plane upward, forming a semicircle in the air. So, if the radius of the semicircle is 112.2 meters and the airplane's speed is a constant, 73.3 meters per second, what is the centripetal force on the plane? So we're going to use the centripetal force equation. We'll just plug in, so this is a plug and chug. Plug 455 kilograms here. You plug in 73.3 meters per second for velocity, and then you square that. Plug in 112.2 meters for the radius, because it tells you that. And then type it all in. And then you get, when you type that all in, hopefully you've done it. Stop the video and do your work if you haven't, and then you can check your answer. So I get 2.8 times 10 to the 4th newtons. Force is a vector. We've had a lot of trouble this year not putting our direction. So in which direction is force pointed when you're in any sort of circular motion? Well, it's always toward the center of the circle. So toward center of circle. You must put a direction for force. It's a vector. Okay? And we know that direction. We know acceleration and force are pointed toward the center of the circle. Velocity is pointed tangent to the circle, or speed if it asks for it. Speed doesn't have to have a direction, I guess. Number 2. Oh, I've written one of these, guys. They've kind of outlawed them, I think. But a popular amusement park ride is made of a hollow cylinder that spins. People stand against the outer wall. They get it spinning fast, and then they drop the floor out. So you're just stuck to the wall with nothing below you. It's really fun. Sorry, you can't ride one now. People don't fall down because they feel stuck to the wall of the cylinder. This is because the friction that's created by the wall pressing the people holds them up, keeping them from falling, despite the fact that there's no floor to stand on. If the ride has a radius of 5.1 meters and spins with a speed of 15.1 meters per second, how much centripetal acceleration do the riders experience? All right, so we're going to use this equation that I halfway erased. We'll do number 2 down here. Let's see if the black marker works. So it's v squared divided by r. So the radius was 15.1 meters, v squared, divided by r, which was, meters per second. V squared, meters per second, divided by 5.1 meters. All right, so type in 15.1, square it, divide by 5.1. You've got 3 sig figs in the top, but only 2 in the bottom, so you can only keep 2. So that's going to be 45, and it'll be meters per second squared once you cancel one of the meters with the other. Remember that acceleration is a vector quantity. We know that force and acceleration vectors for circular motion point toward the center of the circle. So toward center of the circle, ECC will be our direction, I guess. You can't just give me a positive or a negative because that doesn't really describe that very well, does it? I'll just do one more and then we'll stop that video and get a new one going. All right, so number 3. A child attaches a 34.5 centimeter string to a 15-gram ball and starts to swing it around his head. He twirls it faster and faster, and when the ball gets to a speed of 12.1 meters per second, the string breaks. What was the maximum tension the string could withstand? So we know it'll be a tiny bit less than what we calculate, right? So we'll look at centripetal force. Fc equals mv squared over r. So the only thing providing centripetal force in this little toy is the tension. So we know that F sub c is equal to tension. So mv squared over r is what we're going for. we can say tension is mv squared over r. All right, so it gives us the mass of the ball as 15 grams. We know for using newtons and stuff, we have to convert that to kilograms. So that'll be 0.015 kilograms times velocity squared. So velocity was 12.1 meters per second. That quantity squared. The radius was 34.5 centimeters. Of course, we know we have to convert that to meters to be using newtons. So that's 0.345 meters. So mv squared over r. If you type that all into your calculator, you should then get tension equal to, what, 6.37 newtons? Right, because we're in kilogram meter square, or meter per second squared. So newtons, 6.37 newtons is what I get. Hopefully that's right. And we'll start with number 4 on the next video.